Hello everyone. Have you ever wondered what invisible magic surrounds a simple wire carrying electric current? It turns out that wire creates its own little magnetic world. Here's a fun start. Why did the electron break up with the magnet? Because it found the relationship too attractive. Now, when a straight conductor carries current, it doesn't just quietly let the electrons flow. It sets up a magnetic field all around itself. Imagine concentric circles hugging the wire. This magnetic field forms perfect circles on planes perpendicular to the wire. And to find out which way the magnetic field lines twist, we use the right-hand rule. Point your thumb along the current direction, and your curled fingers show the magnetic field's direction. According to the formula, the magnetic field strength at a distance r from a long straight wire carrying a current I is given by B equals μ0 times I divided by 2 pi times r, where μ0 is the permeability of free space, a constant equal to 4 pi times 10 to the minus 7 Tesla meter per ampere. Notice how the field strength drops as you move further away. Specifically, it decreases inversely with distance, meaning if you double the distance, the magnetic field halves. This decreasing strength forms a cylindrical symmetry wrapping around a wire, like invisible rings of influence. Permeability μ0 is the magnetic personality of free space here, serving as the proportionality constant linking current and magnetic field. In the diagram, you can see a vertical wire with circular magnetic field lines around it. The radial distance r is marked from the wire outward, and the current direction is shown as well, helping you visualize these invisible magnetic circles. So next time you see a plugged-in appliance, remember that each wire carries its own spiral of magnetic field lines, all thanks to this fascinating physics. Welcome back. Here's a curious thought. What do you think happens if we bend that straight wire into a circle and flow current through it? That's right, we get a magnetic field that is even more interesting. It's like the wire is throwing a little magnetic party right at its center. A circular loop of current produces a magnetic field that points perpendicularly, straight out or into the plane of the loop, exactly at its center. Think of the loop as a tiny magnet with its magnetic field neatly concentrated in the middle. The formula here says that the magnetic field at the center of a single circular loop of radius r carrying current I is B equals μ0 times I divided by 2 times r. If you turn it up a notch by having n turns of wire coiled together, the field scales up linearly to B equals μ0 times n times I divided by 2 times r, showing how multiple loops strengthen the magnetic effect. You can picture this as each small segment of the loop producing its own tiny magnetic contribution. All these vector contributions add up in perfect harmony, summing into that straight, vertical magnetic field arrow you see at the loop's center in the diagram. The radius r is labeled, and the current flows in the direction indicated, helping you see how the magnetic field intensity grows with both current and number of turns. This is the very principle behind electromagnets: more loops, stronger magnetic field. So those cranes lifting huge cars? They rely on this simple but powerful loop of current trick. Hey there, physics explorers! Let's step away from the loop's center and ask, what happens if we move along the axis passing through the loop's center? The magnetic field doesn't just vanish, it changes, and we can predict how. Using the Biot-Savart law and integrating the tiny contributions from every bit of the loop, the magnetic field at a distance x along the axis from the center is given by B equals μ0 times I times r squared divided by 2 times the quantity r squared plus x squared raised to the power of 3 halves. If we plug in x equals 0, we gracefully return to the earlier formula for the field at the center. B equals μ0 times I divided by 2 times r, confirming our math is consistent. But as you move further away, meaning larger x, the magnetic field weakens rapidly, showing how the magnetic effect is mostly localized near the loop. Picture the diagram, a side view with the circular loop lying flat, radius are labeled, and the point at distance x on the axis marked clearly. The magnetic field direction is drawn, helping you imagine how the field lines stretch out and weaken as you move away. This tells us that magnetic fields from loops are strongest around the center and fade with distance, incredibly important for designing devices like MRI machines where field localization matters. Magnetic fields love to stay close. Hello again, curious minds. Now I have a tiny but mighty secret for you, the Biot-Savart law. It tells us precisely how a small piece of current-carrying wire, called an element dl, creates a small magnetic field dB at some point in space. The law states that dB equals mu0 divided by 4 pi multiplied by current I times the vector dl crossed with the unit vector r hat, all divided by r squared. That's a mouthful, so let's unpack. The vector dl is a tiny segment of the wire, r is the distance from that segment to the observation point, and the cross product means the magnetic field direction is perpendicular to both dl and the line joining that element to the point. It's like a tiny invisible propeller generating a magnetic whirl at right angles. When you add up contributions from all such tiny elements, especially those symmetrically arranged, the fields combine into the neat patterns we saw earlier around wires and loops. You see the small current element dl, the position vector are extending to point P where the field is measured, and the magnetic field direction dB shown via the cross product. This visual helps you grasp the vector nature of magnetic fields right at the source. Remember, this fundamental law is the nuts and bolts of magnetic field calculations, even if the math can get tricky for complex shapes. Welcome back, physics detectives. Now that we know about tiny current elements, let's talk about how Ampere's Circuital law makes life easier for certain symmetrical situations. Ampere's law connects the total magnetic field around a closed loop to the total current passing through that loop, neatly summarized as the line integral of magnetic field B dot dl equals mu0 times I enclosed. What this means is if you trace a closed path around the wire and adapt the magnetic field along it, you get a value proportional to the current inside. For a long straight wire, symmetry helps because the magnetic field strength is constant in magnitude along a circle centered on the wire, turning our integral into a simple multiplication. This brings us right back to B equals mu0 times I divided by 2 pi times r, the familiar magnetic field for a straight wire. Ampere's law is especially helpful when dealing with shapes too complex for easy integration using Biot-Savart. Just remember, only the net current enclosed counts. If there are currents outside the loop, like a return wire nearby, their fields cancel out in this calculation. In the diagram, see the Amperian loop drawn as a circle perpendicular to the wire with magnetic field tangential to it, a small segment dl marked, and current flowing into the page. This picture shows how symmetry lets us use line integrals to solve magnetic field problems efficiently, saving time and headache. Alright, let's put theory into practice with a quick example. Suppose you have a circular coil carrying a current of 5 amperes with a radius of 0.1 meters and it has 20 turns. What is the magnetic field at the center? We use the formula we learned earlier, B equals mu0 times number of turns and times current I divided by 2 times radius r. Substituting the values, mu0 is 4 pi times 10 to the minus 7 Tesla meter per ampere, n is 20, I is 5 amperes, and r is 0.1 meters. Plugging that in, the magnetic field comes out to be equals 4 pi times 10 to the minus 7 multiplied by 20 multiplied by 5 divided by 2 times 0.1, which calculates to approximately 6.28 times 10 to the minus 5 Tesla. And converting units, That's about 62.8 microtesla, which fits nicely into expected ranges you'd see in typical lab experiments. The diagram shows the circular coil with notation indicating the field at the center, helping you picture the geometry and the direction of the current flow. So next time you see coils in electromagnets or inductors, remember how stacking turns cranks up the magnetic field power. Let's wrap up the fascinating magnetic world of current-carrying conductors. The magnetic field around a straight long wire is given by magnetic field strength B equals mu0 times current I divided by 2 pi times distance r. For a circular loop at its center, the field is B equals mu0 times I divided by 2 times radius r. Moving along the axis of that loop at a distance x, the field becomes mu0 times I times r squared divided by 2 times the sum of r squared plus x squared raised to 3 halves. Ampere's Circuital law connects the magnetic field around a closed loop to the current it encloses, expressed as the integral of B dot dl equals mu0 times enclosed current. The magnetic field direction follows the right-hand rule, and its magnitude can be computed either by the Biot-Savart law for fundamental elements or by symmetry considerations using Ampere's law. Remember, the magnetic field strength diminishes as you move away from the wire or loop, reflecting their circular symmetry. Coils with multiple turns increase the magnetic field linearly, which is why electromagnets are so effective. Key ideas like field localization, symmetry, and superposition help us understand real current configurations in devices ranging from electric motors to MRI machines. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.